Gianco, please example 4.3-5, insulating an electrical wire and critical radius. We are given an electric wire having a diameter of 1.5 mm and covered with a plastic insulation. The thickness of the insulation is 2.5 mm and exposed to air at 300 Kelvin. And we are given also here with a convective heat transfer coefficient of the air is 20 watts per meter squared Kelvin. The insulation has a conductivity of 0.4 watts per meter per Kelvin, and it's assumed that the surface temperature of the wire is at 400, no matter if it's insulated or not. We are being asked to calculate for what will be the critical radius, letter B, the heat loss per meter, not per, but per meter of wire length with no insulation, and what will be the heat loss if there will be insulation. Okay, allow me to draw first or sketch the problem. Okay, so essentially this will be our wire with no insulation, or we call this bare wire, no insulation, and the other wire has insulation with it, that green one. Of course, this is not drawn into scale. And in this case, let me draw the cross section. How will it look like, so that we'll have a better view of the problem. Okay, the cross section will look like this one. This one is a bare wire with no insulation. The temperature at the surface is at 300. Okay, let me label that as, okay, let me label this as T1. Okay, the temperature at the surface, and the surrounding is actually at 300. T surrounding. Okay, this is at 300 Kelvin, and actually heat flow from the surface towards the surrounding. Okay, and this will be convective, and in this case convective heat transfer, Q will just be equal to HO AO delta T. Okay, in which HO here is already given to be 20, and AO is simply, well, AO is simply, well, what will be the area of this one? The length is supposed to be per meter, per wire length of 1 meter. So the length is 1 meter, and this will just be of radius. It will be the radius of this. Okay, the radius of this one. We call that R1. Shall we say R1? R1 in this case is just, the wire has a diameter of 1.5 mm. So half of that essentially will be, well, 1.5 over 2 mm, and then convert that to meters. Essentially you will have R1 to be equal to 0.75 times 10 to the negative 3 meters, and area in this case, that will be the area of that exposed, because this area will be this area exposed to the air, and the area for this one now, AO, is just equal to 2 pi. In this case, the outer radius will be R1, 2 pi R1 times the length, which is 1 meter. So substituting values for that, that will give you, this will give you an area of the surface area of a bare wire, 1 meter long of a bare wire, is 4.712 times 10 to the negative 3 meters squared. And what I'm calculating really is letter B. Now, what will be the heat loss per meter of wire if it's bare? So multiply that by 4.712 times 10 to the negative 3, and multiply that further by delta T. Delta T in this case, temperature of the surface of this bare wire is actually at 400, supposed to be at 400. So this is 400, so the driving force delta T will be 400 minus 300, essentially 100 Kelvin of driving force of temperature difference. In that case, that will then lead to Q, which is equal to 9.42 watts. Okay, that's Q essentially, which means that if this wire exposed to that air with no insulation, it will be releasing 9.42, or radiating, or not really radiating, it will be releasing to the air by convection 9.42 watts of heat. Okay. Now let's now take a look on letter C first. Okay. What will now happen if we insulate the wire? The purpose of insulating electrical wire is not really to prevent heat transfer, but actually to prevent you from being electrocuted or touching barely the live wire. So in this case, let's try also to take a look on what will happen to the heat transfer potential or capability of that wire. Now, if we put some lagging or insulation into it, what will happen is that it is assumed first that here at the surface of the wire, it's still at 400, okay? We still call that T1. However, the one now exposed to the surrounding air is not that one, but this one, the outer layer of the insulation, okay? And therefore, the thing is, it need to pass through. The heat transfer will be from the surface of the wire, of that wire, to the outer surface of your insulation, and from that insulation outer surface to the air. Okay. So there are two steps now: conduction followed by convection. Okay. So this will now be lumping that two process, okay? And conduction, in this case, conduction will simply be, well, this is conduction through cylindrical shell, and it's easy to calculate for Q for that, right? Q will just be equal to delta T, the difference in their temperature, over the resistance, okay? And for this case, since we are actually we don't know the temperature of the surface of this wire, it's not equal to 300. 300 is a temperature of the surrounding air. It's not equal to that. So it's difficult to directly compute Q using this. But what we can do is we essentially have now um, resistance in series. The first one is the conduction resistance, and the other one will be the convective resistance. So essentially, it looks like this one now. Okay. This one is at 400 Kelvin. This will be T1, and this one is at 300 Kelvin. Wait, I'll put it at the top. This one is at 300 Kelvin. This is a temperature T surrounding. Now we don't know yet at the temperature of at the middle, but we don't really care for that because we could lump this into one resistance. Then we can then solve for what will be Q passing through this resistance. We can solve for Q if we are able to get the overall resistance for this. Okay, let me just have this, that this will be the resistance by the conduction through this insulation, and the other one will be the convective heat transfer or convective resistance. So this will still be T1, and here it will be Ts. Q will then just be as easy as, this is R total now, delta T over, let me just put it at the top. So if this is R total, then Q will just be solved if we can just get R total. So not really much of a problem really. So let us first calculate for what will be the R given by this insulation. Okay, what will be, like, let's call this RA, and this one RB, the resistance offered by the air. RA is simply, since it's a cylindrical wall, will simply be the thickness of that wall over the conductivity of that insulation, K. Then we have area log mean. Okay, and how do you compute for the area? Well, the area log mean here is this insulation. The inner insulation has an area of well, that area of the inner insulation is just actually 2 pi Ri, the inner I in this case, which is equivalent to 0.75 times 10 to the negative 3. So from here to there, that's 0.75 times 10 to the negative 3, and that's, so it's relatively, it's already been calculated, right? It's already been solved. It's equal to this times L. It's 4.712 times 10 to the negative 3 meters squared. The only problem is what will be the AO. Now, we are given that the radius or the diameter is actually, or the radius of your wire is 0.75 times 10 to the negative 3 meters, and the insulation is actually 2.5 mm thick, which means that the outer radius will simply be just the inner radius plus that of the, so that will just be 2 pi r1. This inner radius is actually the radius of the wire, which is 0.75 times 10 to the negative 3. And then you add the thickness of the insulation. In that case, thickness is given to be 2.5 mm, or that will just be plus 2.5 times 10 to the negative 3, and then the length is just 1. Essentially, the outer radius, the outer area for this setup will be um 0.02042 meters squared. And how do you get the area log mean for this? Well, we just have that area log mean in this case will be AO minus AI over ln of AO over AI, where AO or AI are this one, which refers to the inner and the outer area of this green insulation. In that case, area log mean AO minus AI will, or evaluating, putting all the values will give me, it gives me a value of 0.01071 meters squared. Okay, so let me have that. And putting the values, well, delta R is simply the difference or simply the thickness of the insulation. It's actually given to be 2.5 mm thick, so 2.5 times 10 to the negative 3 over K of the insulation is supposed to be given as zero point 0.4 watts per meter Kelvin. So 0.4, and then the area log mean given by that 0.01071. That will give me an RA. The resistance of this insulation will be, it's equal to 0.58. Okay, wait, doesn't look good. Okay, RA is equal to 0.58. Now, how about RB, the resistance offered by the air which undergoes convection? Now, similarly, for air, or actually for in forms of resistance, one could just remember that R for that, RB in this case, let me change color. Okay, so if this undergoes convection, so that will be Q, supposed to be, will just be what? HO, area outer in this case, times delta T. So if you equate that, try to find the resistance, supposed to be, this must be the same as delta T over R, in this case RB, we're looking for. So essentially RB is just equivalent to 1 over 1 over RB is just HOAO. So HOAO. And I think we know HO. What we are given that, well, the over heat transfer coefficient, convective heat transfer coefficient is 20. So that's 1 over 20, and we know AO, the outer. So in the first problem, AO is just 4.72. But in this case now, since we put the insulation, the outer area is exposed to the air is quite bigger already. It's 0.02, okay? 0.02042. And in that case, RB will just be, okay, in this case, 2.4486. So as you can see, the resistance offered by the insulation, by the added insulation, is quite lower than the resistance offered by the air. That's why, in this case, Q will just then be, let's finalize our answer. Q will just be delta T. In this case, we know delta T, right? It's still, oh wait, let's calculate it for R total. R total now will then just be equal to RA plus RB. RA is 0.58, RB is 2.4486. Okay, we are getting 3.029. Okay, that's our R. And then to calculate for Q, this time this is the Q that what will be the heat that will be lost if there will be insulation. Delta T is still 400 minus 300. That's 100 Kelvin over 3.029. That will give us a value which is close to 33 watts. Okay, approximately 33 watts. As you can see now, well, if there's no insulation, the heat that will be released to the surrounding air is only 9.42, but with the added insulation, oh, it's quite counterintuitive. Like, oh, why is it that the heat loss, more heat is transported, or meaning more heat is released if there's insulation? Even if your insulation has low conductivity, take a look. The insulation is only has a conductivity of zero point 0.4. The thing is, even if you add more resistance to it, the area exposed to convective heat transfer, which in this case, the convective heat transfer coefficient is quite low, only 20, and as you can see, the resistance offered by the air is high, 2.4, while the resistance added when you put onto the insulation is quite low, only 0.58, and meaning the increase in area, as you can see, AO here is just 4.72 times 10 to the negative 3, while here it has increased. Okay, it's now 0.2. This is 0.0047, so like roughly 4 times increase in the surface area exposed to the air. Now, this is not the time that we will try to go back to the idea of what will be the critical radius, calculating for the critical radius. So that's letter A. Okay, critical radius. The critical radius R2, meaning this is the radius of the insulation. Critical is just given by the equation H over K, HO over K. HO is the um, convective heat transfer coefficient, normally of the air where it is exposed to. In this case, it's 20. K is the conductivity of the insulation. In this case, K is simply zero point 0.4. In that case, wait, I think I made a mistake. It's supposed to be K over HO, not the other way around. Okay, so I'll just put here the raised to the negative one. Supposed to be R will just be K over HO. So raised to the negative one. That will supposed to give me, if placed with proper unit, it will supposed to give me 0.020 meter, or it's equivalent to 20 mm. What does this say? Because H, yeah, it's 20 mm. It means that if your insulation will give you a radius smaller than 20 mm, adding that insulation will increase the heat transfer. But if the insulation will lead to, or the radius of your wire is already more than 20 mm, adding insulation of course will make the R2 will be greater than the critical. That means if you have a wire which is quite big already, for example, you have a wire this big, like a wire which is 1 meter in, no, 1 meter in diameter, or the radius is 1 meter. Of course, there's no wire like that, but this is what happens if you have a pipe. Your pipe material is already quite big, and putting insulation to that material will what? Will will not increase the heat transfer, but will prevent heat from flowing out because you are already far more than beyond the critical radius. So as you can see, critical radius normally is only be this this big, 20 mm. Normally because HO is dependent on the air that we have, normally at 20, and the conductivity will not go beyond that one. So that's it.